In this goal, we're going to talk about metallic bond characteristics. So we've looked at ionic and covalent, and in covalent, we know that a covalent bond is a nonmetal to a nonmetal. And we've looked at ionic, and this is a nonmetal with the metal. Well, what's the other combination? It's metal to metal. And so this is the metallic bond that we're talking about. When you look at metals, we find that they only have a few outer electrons. So they can have one or two valence electrons. There are some metals in the p block that have a few more there, but they're kind of oddballs. Um, in metals, all the atoms have the same attraction for all the valence electrons. There's no tendency to give up or gain electrons like you would see in a nonmetal or a metal. And so what a metallic bond is, that the valence electrons, they become delocalized. And these delocalized electrons are free to move around throughout the material. So when the valence electrons are lost, then what is left is a cation. So every cation is floating on these delocalized electrons. And they describe the metallic bond as positive ions floating in a sea of electrons. It's called the electron sea model. Again, each electron doesn't belong to any one atom. So you'll see that it will move around throughout the substance, just flowing through from cation to cation. Um, a metallic alloy are different metals melted together, and the reason why this happens is to make the metal stronger. So for example, if you have a piece of gold jewelry, it's probably not pure gold. Gold is a very, very soft metal, and so to make gold harder, they will melt other metals in with it. Well, what's holding that gold to the other metal that they've added? It's a metallic bond. So the metal that they've added will add its delocalized electrons to the mix, and it will cause the gold alloy to become stronger. Another name for delocalized electrons are free electrons. Unlike ionic crystals, when metals are hit by an external force, instead of the metal shattering, it just is deformed. And this is because those cations are floating on those electrons. In fact, all the metallic characteristics are due to these delocalized or free electrons. So we have that metals are very hard, they are malleable, which means you can bend them into shapes. They're ductile, meaning you can pull it into a wire. They will conduct a current in any phase as a solid, liquid, or gas. And again, all these properties are due to the delocalized electrons. Down here at the bottom, I have a picture showing those delocalized electrons, how they kind of flow from cation to cation. But if you put it under a power source, you will see that those electrons will flow. So for example, if I have some sort of electrode here and one here, those electrons will flow away from the negative and towards the positive. And this will complete the circuit, and they will be able to carry that current. Metals are the only substance that will conduct a current as a solid, and that is because, again, to carry a current, something has to be able to move. And in this case, it's those delocalized or free electrons. The more delocalized electrons there are, the harder the metal becomes. So if you look at group 1, your alkali metals, these metals are so soft that you can cut them with a knife. In group 2, the alkaline earth metals, they're a little bit harder because there are 2 valence electrons. And in your transition metals, this is where we find the hardest metals. And this is because the d electrons can become delocalized also. So adding to the number, instead of just having 2 valence electrons become those delocalized electrons, the transition metals have their d electrons also become involved. Metals, they have higher melting points than covalent solids, uh, but probably not as high as the ionic solids generally. Of course, there's always exceptions. How you can tell the hardness of the metal is by looking at the number of delocalized electrons. So those alloys that we were talking about before, if you have a metal that only has one or two delocalized electrons, to make it harder, you might want to add a transition metal that will have more than that, that will lend its hardness to the alloy. Let's classify ionic, metallic, and covalent bonds in order by strength. And that's the order they go in. Ionic is the strongest, metallic is in the middle, and covalent is the weakest of these three. How these are determined are by looking at something called bond dissociation energy. And we find that breaking that ionic bond takes a lot of heat. And so because the melting points are so high for ionic substances, that lets us know that that is the strongest bond. So let's classify 1, 2, 3, and 4, each of these as being either ionic, covalent, or metallic, and then we will go ahead and rank them. So number 1, we have a metal with a nonmetal, so this is ionic. Number 2, we have two nonmetals. This is actually a nonmetal bonded to itself. This is covalent. And number 3, it looks like it's covalent because we have something bonded to itself, but don't be fooled. This is two metals. So a metal to metal, this is metallic. And then number 4, I have two nonmetals, a nonmetal with a nonmetal. So this is another covalent. So as we classify these, we know that ionic is the strongest, metallic will be next, and covalent will be the weakest. So looking at our list, we have our ionic, just happens to be listed first. It is the strongest. Make sure you pay attention that that is the order to put it in. So ionic is the strongest, metallic is the next strongest in strength. And then we have covalent. Notice I have two covalent. So when you have a choice between two, then you go with this second rule. The greater the difference in electronegativity, the stronger the bond. And it goes for covalent bonding too. So that's why I scribbled the ionic out. So we have covalent, two covalent bonds here. So we have one bonded to itself. That has no difference. That's completely the same pull on the electrons in that bond. So that's going to be our weakest bond. So that means that this other covalent bond will be stronger. And it is the one that has the greater difference because I have two atoms of two different elements. So they're going to be similar in that they're going to still be sharing, still have quite a strong pull, but that difference is going to be really low. Let's look at this example here on this slide, and I want you to stop the video and try this out for yourself, and then you can start it to see if you're right. Okay, again, we're going to go through and identify if they are ionic or covalent or metallic. And so let's start at the top. I have a nonmetal, which is hydrogen. Even though hydrogen is hanging out above the alkali metals, it is a nonmetal. So don't forget that. So we have a nonmetal and a metal. So this one would be ionic. Next we have, again, a nonmetal and a metal. This would be ionic. Then we have hydrogen and hydrogen. So this is a nonmetal and nonmetal. This would be covalent. And last but not least, we have lithium and lithium. And this is not covalent, it's not sharing, this is a metal. So this would be a metallic bond. So let's go through and classify this. And it's asking for weakest to strongest. So we're going to go covalent to metallic to ionic because we know that ionic is strongest and covalent is weakest. And that's the order that we need to put these in. So there's only one covalent, so this one is the first one. Next, metallic, only one metallic is right here. And then we have our two ionic. So again, we rank strength by difference in electronegativity when you subtract the values. So you could go and look at the values, but I see that lithium is above potassium on the periodic table, so it should have a higher number. My potassium should have a lower number. And so my greatest difference is going to be with that potassium. And so I'm going to have that as my strongest bond. So that would be the fourth. And so that would make the lithium hydrogen come in as the third weakest. So we've talked about three different types of bonding: ionic, covalent, metallic. And so you should have this information in your head, knowing the difference between the bonding. So if I asked you a question such as, what bonding can conduct a current as a solid? and you would say metallic. What substance is a good insulator? You would say covalent. What is the bond between a metal and a nonmetal? That would be ionic. So that's the type of information that you need to know. In the lab, we are going to be looking at these three types of bonds and figuring out how to separate substances using what we know about how metals act and how ionic solids act and how covalent solids act. And so this information I will post up during the lab so you can refer to it as just a guide.